Okay, so we're back on 3.3 derivative rules, and just wanted to recap where we're at here. We just finished up doing the quotient rule and with a graph, and now we are picking up with derivative rules. And we have it's possible to use the quotient rule to extend the power rule to find the derivatives of functions of the form x to the k, where k is a negative integer. So we would often just rewrite the negative integer or the expression with negative integers. So we'll start off, there's a video here, you can watch videos where we see those links. But here we want to find the derivative with respect to x of x to the negative fourth power. And so you can see I draw the arrow to the rule. K is equal to negative 4 here. It's just the power rule, except k is being replaced, k is a negative integer. K is replacing n in the power rule. So here we have a negative 4, and then we have x to the negative 4 minus 1. So we got negative 4x to the negative fifth power. But we often rewrite that with positive exponents, so we're going to rewrite that as negative 4 over x to the fifth. One of the mistakes people make is they think that a negative exponent will make the expression negative, and therefore this would be some kind of a positive, but it's not. That's exactly what the negative 4 goes in the numerator, and then the x to the negative fifth goes to the denominator as x to the fifth. Okay, use the extended power rule and the constant multiple rule to find the derivative of f of x is equal to 4 over x cubed. So I'm going to do a real quick rewrite there and then use the power rule and the constant rule, pulling the 4 out front and then using the power rule. So it looks like I get negative 12 x to the negative fourth power. And so I'm going to rewrite that as negative 12 over x to the fourth. Okay, and there you go. So that's a little rewrite that you often do with negative exponents. Okay, combining differentiation rules, we can find the derivative of any polynomial or rational function by combining differentiation rules. A good rule of thumb to use when applying several rules is to apply the rules in reverse of the order in which we would, of course, evaluate the function. So when we look at the next example here, we have k of x, and I went ahead and I just did this one because I thought it was kind of easy to see, where you have the constant multiple rule for 3 times h of x, and then we have a product rule for x squared times g of x, and we want to find k prime of x. So this is what it's going to look like then. Noting that sometimes we'll go ahead and do the product rule and we'll kind of forget where we are, and if there's something that comes after it, you're like doing all this stuff, and then sometimes students will forget to continue with some other function. But we have the 3h of x that comes first, so we did that, took care of that, and then handling the product rule. I have the first function is x squared, the second function is g of x. So recall that I said I handle this by saying first dir second plus second dir first, like so. And it has just always worked for me that way. Little mnemonic devices. Okay, and then the next one we have is, I'm showing you this because I could prove it using, if I wanted to prove k of x is equal to the product of 3 functions, and I could express k prime in terms of those 3 functions, and I could prove it using the product rule twice, but I'm going to forego that, and I'm just going to say, given that j of x would be like f times g, and then I could say j prime is f times g prime plus g times f prime. So the function and the derivatives alternate, right, per product. And so the same thing is going to happen here, where you have k prime, if k prime, I think I need to write something else though, if k of x is equal to f times g times h, all functions of x, then k prime is equal to that line here that you see, that f g h prime, f g prime h, and f prime g h, and that's the rule. Okay, and then we have an example here where you have, here's my low D high rule here. And this is an example where if I have some kind of complications, I like to pull it out, and you can see that I have this up here, the derivative of 2x cubed k of x. So I have a quotient rule, though. H prime of x is what I'm looking for when h of x is defined as that quotient. And so I'm going to set it up so I have low d high, less high d low, over low squared, and away we go. So I've got 3x plus 2, then I replace the derivative. So you can see that I did the derivative up high. Let me get the highlighter here. And I have the derivative done so you can see that it is all this stuff, right? So first or second plus second or first. And I think most importantly, and then, oh, let me do one more thing. Here we have a 3 here, the derivative of 3x plus 2. So low d high, less high d low, over low squared, and away we go. Now, in my opinion, I could multiply this all through. I think it's the action of setting this up that I wanted you to go over the most. Just dealing with that fact that this derivative of 2x cubed k of x was embedded in this quotient rule. So sometimes it is easier if you just take it out. I think the ROI on this is not going to be significant to continue it, but I'll leave the answer in the note answers in Canvas. All right, so then you have this number 4. This is kind of an easy little difference. It's just going to be the constant multiple times the derivative rule for both of those functions. And you have 3f prime minus 2g prime, and done. Okay. And then now in this next one, I left this on here. I was going to erase this. I was kind of working ahead and then forgot to erase it. But so determine the value of x for which this function has a horizontal tangent line. So you have to say, well, what do we know about this? What do we know? And the thing that we know is that a horizontal tangent line looks like these two graphs, like where you see the tangent lines. So the slope is 0 at those points, okay? So we say, all right, well, there's f prime. We calculated f prime in the first step. And then after we do that, then we set it equal to 0. And since I thought, does it factor? Yeah, it factors. So I've got it factored. And then I use the principle of zero products and say, well, one factor is equal to 0 or the other one is. And I come up with 2 values. So f of x has horizontal tangents at those 2 locations, 2/3 and -4. So now what do we have? We have example number 6, right? So with that, on number 6, so we have the concentration of antibiotics in the bloodstream T hours after being injected is given by the function C of t is equal to 2t squared plus t over t cubed plus 50, where C is measured in milligrams per liter of blood. So, and most of the time it makes sense when we think about medications, that medications decrease in the bloodstream after time. So you can see that with this particular function, with this particular function, you can tell that as t goes to infinity, C, the concentration goes to 0. And that would make sense. So then we've got the quotient rule we're going to handle this with. So when we are doing the quotient, I'm going to erase this stuff here. When we're doing the quotient rule, we're going to say t cubed plus 50. So we're going to say low d high. So it's going to be 4t plus 1 less high 2t squared plus t. And d low would be 3t squared all over t cubed plus 50 squared. Now, we're going to try to find C prime of 12, and we could go in and we could simplify this. I'm going to give you the simplified version for this after it's multiplied through. This is what I get. Negative 2t to the 4th minus 2t cubed plus 200t, and then that's going to be plus 50, and then that's all over the quantity t cubed plus 50, and that's squared. So we want to find this C prime of 12 and then interpret the result of this thing. And as it turns out, I'm not sure I really want to do the whole thing, but yeah, I guess I could. I'm going to plug it in. And then you could then, of course, get your calculators out and confirm or verify when you do this. But I would take and get my simplified version into this. And I have 12. What do we have here? Negative 2 times 12 to the 4th minus 2 times 12 cubed plus 200 times 12 plus 50. Okay, so we have that there. And this is over 12 cubed plus 50. I have to double check the results for this one squared, right? I want to check these, but this is what I get. So negative 0.0134, and that's in milligrams per hour. So remember I said about the Leibniz notation, it's kind of convenient sometimes because it's in that fractional unit kind of form where I would say the concentration in milligrams per dt time in hours. So it's just a reminder what you should have there. So it's decreasing at 134 10,000ths milligram per hour. Okay. All right. So move on to the next one. The position of an object on a coordinate axis at a time t is given by s of t. So we're going to have to use the quotient rule with that. Actually, we could use the product rule if we use negative exponents, but I'm just going to go ahead and use the quotient rule. All right, so I have s prime. The velocity, it says the position of an object on a coordinate plane is given by s of t. What is the initial velocity of the object? So remember, initial velocity is at time t equals 0 as a standard. So I've got the velocity here. S prime is equal to low, d high, less high, d low, over low squared. So I'm going to simplify this. So it looks like I get t squared plus 1 minus the t times 2t. And then that is all over t squared plus 1 squared. So it ends up to be equal to, so I'm going to say the velocity s prime of t is then equal to 1 minus t squared. Since it's a t squared plus 1 minus 2t squared, that's what I'll get. And then over the t squared plus 1 squared in the denominator. And then I want to know, what is the initial velocity? So the initial velocity at time t equals 0 is equal to s prime of 0, which is equal to 1 minus 0 squared over 0 squared plus 1 squared. So it looks like we get 1, and the units in this case are not really being spoken about, so you can think of it like 1 centimeters per second or something like that. But we just have the initial velocity here without units, so just a scalar. And then for number 8, for the following exercises, assume that f and g are both differentiable functions with values given in the following table. Use the table to calculate the derivatives, the following derivatives. So I have laid these out. So I want to make one little correction here. This should be an x. So h prime of x is what I have there. Okay, so I've taken the derivative. So I have a product rule that I have to use first with the x, f of x, and then I have a constant multiple rule that I have to use at the end, and I have those marked. So I want to find h prime of 1. So my suggestion for students is that they put 1 in everywhere they see x. F of 1 times the derivative of x is just going to be 1. And then you'll have the plus 4 times g prime of 1. And now I have my table. I'm going to go back to that and start substituting. 1 isn't going to matter. 1 times f of 1. I'm just going to put f prime of 1. So go to the f prime of 1 and you get negative 1 plus f of 1. F of 1 is 3 times 1 plus 4 times g prime of 1 is 4. And let's see what we get. 18. So we get minus 1 plus 3. So minus 1 plus 3 plus 16. It looks like we do. It looks like we get 18. So h prime of 1 is equal to 18. And there it is. Okay. And then for the next one, we have h prime of 2 with the product rule. And f and g, applying the product rule to f times g. So we have our rule there in the first step, and in the second step, I'm going to plug in 2. So I have h prime of 2 is equal to f of 2 is 5, coming from the table right here. G prime of 2 is 1, plus g of 2 is 3, times f prime of 2 is 7. So it looks like we get 5 plus 21. I believe we get 26 for an answer here. So we get h prime of 2 is equal to 26. I have one more problem to do here, and it is this one. So I have 1 over x, so I'm going to rewrite this as h of x is equal to x to the negative first power, and I'm just going to go ahead and do this product rule with this, okay? So I get h prime of x is equal to negative 1 x to the negative 2 power, so just applying the power rule, plus I have low d high, so I'm going to put g prime of x, less high, g of x, d low, h prime of x. And that's all over low squared, h prime, oh, not h prime, it's just h of x squared. And away we go. So I'm going to rewrite this as negative, well, I'm just going to leave it go. I'm going to just put my answer as with a positive exponent then, okay? Because what do we need? H prime of 4. H prime of 4 is then equal to negative 1 over 4 squared plus h of 4, g prime of 4 minus g of 4 times h prime of 4. And that's all over h of 4 squared. So we get negative 1 over 16, and that's going to be plus. Then I have h of 4, I believe that's 0. H of 4 is 0. I should scroll it down. I'm going to have to go back and forth. 0. And that's going to be times g prime of 4, which I believe is 9. I get scrolled 9. Yep, g prime. And then I've got minus g of 4 is 6 times h prime of 4 is negative 3. I'll just put it in parentheses. And then that is all over 0. H of 4? H of 4 is 0? H of 4? H of 4. I think I have the wrong letter here. Here. Didn't dawn on me just now, until just now. Here we go. No, it's f of x is what is wrong here. So I'm going to make that an f. And we're good to go. So it looks like, f of 4. What happens? F of 4, going to go back and just check my values. I want to make sure that I have the right values here. I have f of 4 is 0. So it looks like I have 0 in the denominator. And I'm going to check the g prime of 4. G prime of 4. G prime of 4 is 9. H prime of 4. H. Wait a minute. Did I do that again? I did that. I got to go back and check it here. I think mentally I'm putting in the F, but let me just put that down as F prime. F prime. F prime. Yeah, that's what I did. I knew which I was using the F, but then I had X. I think we're all right then. Yeah, I think I accidentally wrote the H in there, but okay, we're good to go then. So what do we get here for an answer? We get negative 1/16, but we have a problem here. So this is undefined. So H prime of 4 does not exist. Okay, now hopefully I can get this video in and get started with the next one. Okay, that's it. I will see you when I see you, and hope to see you on Zoom tomorrow night. All right, bye.